You start with those boundary conditions, you come out with Fresnel reflectivity coefficients. Okay, so that's what my solutions to these wave equations look like. And I've got a few things that come out of Maxwell's equations and these wave equations. One is that for wave propagating in free space, the electric field vector and the propagation factor are perpendicular to one another. Oh, maybe I'll just include one more equation here, which we did. S is, help me, Ryan.
C over 4 pi.
Okay, I'll go with that.
So that if you also want to
Plus, probably H.
H, yeah. You'd also want to include mu e and or mu, I guess.
What was that?
You'd also want to include mu, I guess.
In here.
Yeah, mu itself, not mu naught. I think mu would be on the bottom.
Yeah, I think we put mu here. I like that. Seems right, but I don't have it written down for myself. This defines the propagation direction as well, all right? K is parallel to the pointing vector. What else? The direction in which the magnetic field points is perpendicular to K. And
Are E1 and E2 perpendicular to
follows
each
from
other?
this, actually, I can write that E2 is equal to K cross E1 over K. So K hat cross E1.
Divided by K.
So it's the k vector divided by k.
Because K, yeah, it's this. K
Thank you.
hat. But I didn't want to write K hat because you might interpret that as the Z direction. Right? K hat cross E1.
Or
This is the propagation direction. Having done all of this, having said all of this, let me mention that it's not true in plasmas. And if there's time, we'll come back and talk about plasmas. At a particular frequency, when you try to send a plane wave through a plasma at what's called a plasma frequency, then the electric and magnetic fields don't obey these rules this way any longer. What you actually have to consider the polarization of the entire medium. Okay, so for those of you who probably in astrophysics does Professor Roberge address
I think we did a little of that
waves
in
traveling in
optics.
plasmas?
I think we did a little of that in optics.
That's general relativity, and I wouldn't expect them to do waves traveling in
They actually
plasmas.
addressed it in materials engineering courses.
Really?
And in optics a little.
Very free.
Yeah, well, I'll spend a little bit more time on it, if there is time. Oh yeah, what else? And this, I just, Adam asked about it, and I'm just going to mention, this is sort of a statement of fact here. E and D are in phase with one another and in constant ratio at every point. Yeah.
is E1 dot E2 also equal to 0? Or
Yes. Yes. That's
That's implied by that equation.
oh,
buried there.
deeply buried?
These three vectors, E1, E2, and K, are perpendicular to one another.
I thought so.
Because the cross product, the cross product. is
Okay,
0.
now I'm going to go off book for a couple of minutes. What time is it?
25, approximately.
25 after 25.
3:25. 3:25.
Okay, good.
Whenever I just say the minute, I mean after.
All right.
Also 25 till. Well, till the end of class.
And
Convenient.
There are going to be, over the next couple of weeks, several times where I'm going to go off book specifically in order to address applications that you might have need for. So I'm just trying to think. Possibly the next class. Yeah, probably the next class. I'm going to leave waves for a moment and talk about magnetic circuits. Ohanian has nothing on magnetic circuits, nor does Griffiths. But it actually turns out that if you actually want to calculate something, for example, where you might have a chunk of iron like that, and then you put windings around it, and you want to calculate the magnetic field here, you can't actually do that very easily with the techniques that Ohanian has given you. And the electrical engineers have some really nice approaches to solving these kinds of problems. So I'm going to include at least part of a class on that. And right now, I'm going to go off on ways of thinking about polarized light. All right. So usually the strongest interaction of an electromagnetic wave with matter is the electric field with the matter. So we pay attention to the electric field. We care about the polarization direction of the electric field. So that would be my E1. What direction does the electric field go? And so let's consider that I've got a wave which is propagating along, right? And that wave, for a monochromatic wave, is going to have an electric field that looks like that. And by the way, the magnetic field looks like E, if I've frozen in space, then this hand would be the electric field, and this would be the magnetic field. Let's see, of course, what gives me that? Yes. Okay. And then as I move through space, the fields are going to do this. Or if I stay at one particular point in space, the fields are going to do this, cross through one another, like so. I'm not going to do the dance today. I'm not feeling good enough.
It's on YouTube, though.
It is. It's labeled.
But I have my electric and magnetic fields that look like this. And what I'm saying is that for applications, we really care about the polarization of the electric field because that's what interacts with atoms most strongly. So I would characterize this electric field, for example, as I choose a propagation direction. I'm going to propagate this way, that way. And in another class, I'll talk about how you add together waves to the fields that are originating at each point in space to define the direction of propagation. But for now, I'll just define a direction of propagation here. And I'll define, in this case, my electric field is pointing, let's say, in the Y direction. Okay? So this electric field would be E0 Y hat, the real part, for example. No, I've got the imaginary part here. The imaginary part of E, I, K, let's call this X. No, let's call this Z. Then it corresponds to K hat too. Z direction, Y, X, X, Y, that points the wrong way. X points into the board. And X, Y, Z gives me my right-handed system, but I'll just write this as E, I, A, Z minus omega T. So there's an electric field. Any linearly polar, any polarization that I like, actually, can be made up by adding electric fields that are perpendicular to one another, right? So if I want to keep my propagation direction in the z direction, then I could, if I wanted, actually let's take the propagation direction this way. Right now I've got my electric field doing this, just the electric field, right? But if I added to that an electric field which was pointing this way and in phase with it, all right, then the electric field would start here, go to here, go like that, all right, which looks like this. If I add those two together, it points this way. It points this way, like so, okay, if the two waves are in phase. So I can add a second wave to this one, all right, plus E0 x hat, imaginary EPI KZ minus omega t. Let's call this EX and call this EY. Oops, that's stupid. EY, EX. So I've got different amplitudes, but they're in phase. So if I had a little guy here and a big guy here, then I'd end up with a wave that looks like this. Right? Short this way, long that way. A wave that looks like this. It's still linearly polarized. Right? Linear polarization means that the direction, the plane along which the wave oscillates, remains constant. Okay? Here's a really neat thing that we could do. I can take one of these two waves and delay it with respect to the other. Right? Now they're not in phase with one another. Now, when this wave is a maximum, this wave is 0. And then as this one shrinks, this one grows. Right? And then as this one shrinks, this one grows. And then, all right? The net result, yes, George and Eli have got it right, is that in that case, the polarization vector rotates. So if my electric field in the y direction is out of phase with the electric field in the x direction, if they're equal in amplitude and out of phase by pi over 2, then that's circularly polarized light. And we define the direction of polarization such that as it's approaching you, you ask, does the polarization vector rotate? Now, for you, this should be counterclockwise.
Yes.
Is that right?
Yeah.
Okay. So we call that Wittershins. And if, as it's approaching you, it goes the other way,
Sunrise.
then that's diesel. What? Sunrise or diesel? Yeah.
Diesel?
Yes.
With the sun, diesel.
Sunwise I like. I actually like Sunwise and Wittershins the most.
But desol means the same thing.
What?
Desol, as in like towards the sun.
Oh, what do you know? Really? See, live and learn.
So we're not talking about gas here.
Yeah.
What's the first name?
Cool. All right. So I can make light of any simple polarization just by adding up two waves that are at right angles to one another in various phases. All right. If they're not pi out of 2 out of phase with one another, then we actually get elliptical polarization. Okay? The polarization vector still rotates, but it's unequal. It's big this way and small that way. Yeah.
Does the frequency with which it rotates depend if it's circular or elliptically polarized?
No.
What does it depend on?
The frequency, I mean, basically if you think about adding two waves together that have a given frequency, the sum of the two waves will always be the same frequency as the wave that you.
So the polarization rotates with the same frequency that the electric waves
Yeah,
oscillate?
maybe what I'm trying to get at is, or actually, what I have not thought about but I think this is what you're asking, is does the polarization vector rotate at constant speed? Okay. And I'm suddenly thinking not, but that disturbs me. I think it should rotate at constant speed.
Yeah, shouldn't it rotate at delta
2 half.
omega over 2?
I don't know what frequency it is.
I'm still coming off a cold right now.
Yeah, I
So
mean,
I'll get back to you. Yeah,
shouldn't you use the argument that when it's pointing directly up, the other one is non-existent, and the only other time it's going to be that same case is when it's pointing up again? So it has to be the same frequency.
yes, yeah.
Okay.
But I know if you add two sine functions, the frequency of the oscillation is going to be equal to the original frequency. Actually,
No.
it's you can think even in terms of beats.
Yeah.
It's omega 1 plus omega 2 over 2 would be the carrier, and then the difference would be omega 1 minus omega.
And if you
2
change the
over 2.
frequency, you would get depolarization.
Sure. Well, yeah. Actually, now that I think about it, it's got to be that way. Yeah. So, but that's, I mean, in that case, you are adding together two waves that have different frequencies.
Right.
And so, the rules, not the rules change, but the rules, these rules don't apply. Okay. So then we can construct any polarization that we want this way. And one way of writing it, and just, this is for those of you who haven't had optics, is to write my electric vector this way. Because I've got my traveling wave, all right? Then I've got my x component, or x component, the projection of the wave onto the x-axis, and my projection of the wave onto the y-axis. And I put in the e to the I phi's here because these don't have to be in phase with one another, right? If they're in phase with one another, then I've got linearly polarized light. Whatever the relative amplitudes of these two waves is, I'll have linearly polarized light. And if they're out of phase, then I'll have elliptical or circularly polarized light. This way of expressing things, where I pull out the amplitude, I could write this as just like E0 times an e to the I by x, e to the I by y. This thing here is called the Jones vector. And it's a simple way of expressing polarization state, right? If we want to include unpolarized light, for example, and by the way, at any instant in time, light is polarized. It's just that as soon as we start doing time averages, the emission from an atom might be polarized this way at one instant and that way at another instant, or this way at one instant and that way at another instant. Right? So, if we wanted to include those time averages of randomly polarized light, then there's a 4x4 matrix representation that I have just forgotten the name for. I think they're called Mueller indices.
I think that's the crystal plane. No, wait, no. Yeah, it's
No, those
Mueller.
are Miller indices.
Mueller. It is Mueller.
So,
Mueller.
anyway, that describes the polarization of light when it's linearly or linear, circular, elliptical polarization. All right? Vertical polarization would just be written like this. It's all on the y-axis. horizontal polarization. And 45 degrees would be actually, we want it 1 over root 2, 1 over root 2, because we want the length of that vector. It should be a unit vector. So most of the time it's written this way. 1 over root 2, 1, 1 would be 45 degrees. But circular polarization then is easily written as well. And in this case, it would be 1 over root 2, 1 I, and so this is I pi over 2, is right circular. And left is 1 over root 2, 1 minus I. Left circular. And one of the really neat things that we can do is convert right to left, left to right, and linear to circular by adding phase retarders to the system. So for example, I send a particular polarization of light through a material where the speed of light is different for vertical polarization and horizontal polarization. And for example then, well, nothing happens if I send vertical polarization through. It remains vertically polarized because I haven't changed the phase of any two components, right? It might slow down the wave, not slow down, it might phase delay the wave, but it's still vertically polarized. Same with horizontal. But if I go in at 45 degrees, then one of the two phases is going to get delayed with respect to the other one. And if I use what's called a quarter wave plate, then what I'm doing with the quarter wave plate is delaying the x or the y component by 90 degrees or pi over 2. Do that right? Yeah,
yep.
Pi over 2, a quarter wave, because the wave is 2 pi. Pi over 2 with respect to the other way. And so that takes light which was polarized this way and was composed of vertical and horizontal components that were in phase with one another and puts them out of phase with one another. Okay, turning it into circularly polarized light. That's really easy to do. It actually turns out that one of the easiest materials to do that with is crystalline quartz. So it's not just glass, but you need the crystal, but it's really easy to find quartz crystals. You just go out on the beach and there are quartz crystals all over the place. You polish them down and orient them properly, and you have two different speeds of light for horizontal and vertical polarization.
Fun stuff.
What?
Fun stuff.
Yeah, I think it's fun.
Seems cool to me.
Oh, yes. So next class, someone has to remind me to bring my Easter demonstration. I know Easter has gone past, but I have Caro syrup and polarizers, and it's very pretty. Yeah. How many of you have seen that already? Oh, then you don't need to see it. No, there are some people who have not seen sugar water and polarizers. It's very pretty. Okay. So remind me to bring that next class, because that displays where the fun in optics is. The fun in fundamentals. What time is it, Eli?
45 minutes after. 6 minutes left in class.
Okay, I'm going to introduce one more thing. Which is just that thing that I'm talking about, converters. So I want to operate on polarized light. So I've got light that's polarized in a particular direction, and I want to do something to it. Right? I use a polarizer. I use a polarizer or an analyzer. What do you know? And so if I have a device which, for example, only allows polarization along a certain direction. Let's measure it from here as theta. So this is only going to allow components of the electric field which are along the polarizer itself to pass through. And it's easy to make a device that can do that. Again, actually, Polaroid made it first. And it involves getting organic molecules that conduct well in one direction and don't conduct in the other direction. And then you pull them. You actually literally take the film that they're in and you pull it so that the molecules align. And then electric fields, you guys know this really well now, that are along the direction of the wires reflect or are absorbed, one or the other. And electric fields that are perpendicular to the direction of the conducting wires just pass right through. So it's easy to make a polarizer. We put this polarizer in here, and let's say I had light with some electric field that pointed like so, and then what the polarizer does is allow me to select that component of the field that points along the polarizer, right? Where's my, must be in the next page. Oh, there it is. A polarizer at an arbitrary angle acts on these Jones factors, on these polarization vectors, like so. Cos squared theta, sine theta, cos theta, sine theta, cos theta, sine squared theta. Now, light polarized at whatever angle that I want, right, is actually going to be represented, let me make sure I get it straight, by magnitude cos theta sine theta. So this is light that's polarized at some, let me call it theta 1. 2, 2, 2, 2, 2, 2. This is the orientation of the device, of the polarizer. This is the orientation of my incoming light. And then when this acts on that, I end up with the outgoing beam. Give me the amplitude properly, and it gives me the orientation of the outgoing beam. This is all, you could actually do all of this just using Physics 2, Malice's law kinds of rules, right? Where this becomes more valuable is when this device isn't just a polarizer. It could be a circular polarizer, something that introduces retardation into one or the other of the beams. And those are called phase retarders. And I think I'll save the phase retarder for next time. What?
Well, I mean, this was.
I lost yours.